think this is a new record, 6 students in person. It's great. Thank you.
Okay, we'll go ahead and get started. Can the people on Zoom hear me and see the slides?
Yes.
Thank you. Okay, so before we get started today, I just want to remind you what's up for next week. On Monday, we'll do a review for the exam, and then the exam will be on Wednesday of next week. And that'll cover chapters 3 and 4. So today we're going to try and finish up chapter 5. I think we'll get done with it in the class today. If not, then we'll finish it on Monday. There wouldn't be too much left. But mostly on Monday is reviewing chapters 3 and 4 for the exam on Wednesday, okay? All right, so we're going to pick up again with the thermal chemistry discussion we started on Monday. And we touched on this a little bit. We talked about something called calorimetry. And calorimetry is a way that we can measure delta H. It's a way that we can measure delta H, which is, remember we talked about that basically as heat flow. So the instrument that you use to do this is something called a calorimeter. And there's all kinds of these. Like this is an example of one, which is basically 2 styrofoam cups in together to give us good insulation. That's the simplest. I think I mentioned on Monday that next semester you'll do a lab using a setup like this. There's also some more sophisticated ones that we'll talk about in a bit as well. So when we talk about materials, all materials have an ability to capture heat, and that's called its heat capacity. And so heat capacity is defined as the amount of energy it takes to raise the temperature of a substance by 1 degree Kelvin or 1 degree Celsius. Since we're talking about a difference in temperature, and Kelvin and Celsius are essentially the same 100-unit scale, 1 degree change of either of those it can be. So sometimes you'll see it expressed, these constants expressed with regards to Kelvin, sometimes Celsius, it's going to be the same thing. Fahrenheit would be a different story. If it's expressed in terms of 1 gram, then it's called the specific heat, and that's this capital C with the subscript S designates that. So the little s tells you it's specific heat, and that means it's on a gram basis. And then, if that's not confusing enough, there's molar heat capacity, which is Cm, and that's expressing it for a compound on a molar basis. So there's 3 ways that we kind of express this. For the whole substance, there's heat capacity, and that's Kelvin or Celsius change, 1 degree, how much energy it takes to make it change by 1 degree. Then you can express that on a per gram basis, which is specific heat, which is the C with the subscript of S, or on a molar basis, which is the C subscript M. So it's really done all the different ways. The heat capacity itself tends to be more objects and things like this, like if you wanted the heat capacity of the desk. If you wanted the heat capacity of the desk, you wouldn't do that on a gram per mole basis. It would be on a per object basis. So that's kind of the difference there. And depending upon what problem you're trying to solve, there's different ones that are used. So let's take a look at the specific heat equation in a little more detail. So specific heat, in this case, we're saying is the quantity of heat transferred divided by grams of substance divided by temperature change. So in formula basis, that'd be Q divided by M over delta T. We can also rearrange that to solve for Q. So solve for that quantity of heat transferred. And so if we just rearrange that equation, we get Q equals the specific heat times mass times delta T. The reason why this last form of the equation is important is a lot of substances, the specific heat is known. And so there's books that have tables of those values, and you can look that up a lot of times. And you have mass, okay, you would weigh something and get the mass. And then experimentally, you would determine that delta T. That's where you'd use that calorimeter, for instance, is to do the experiment and see what the difference in temperature was from start to finish. And then that would allow you to calculate quantity of heat transferred. So from an experimental point of view, by doing that rearrangement like that, it's a little easier to see how you would use that. Okay, going back to the calorimeter part again, there's something called constant pressure calorimetry. And if you think of constant pressure, if you're at atmospheric pressure, that's essentially constant. Might have some slight variation, but for practical purposes, it's constant. So what you can do is you can use that simple calorimeter that we talked about before, kind of the two styrofoam cups within each other. And the styrofoam is giving you good insulation, so you're not having heat loss, you're containing it and can measure it. And so you can have an aqueous solution and you can carry out your reaction in there and you can measure that heat change. So you know what the temperature was when you started, you run your reaction, you see what the temperature is at the end, and that's your heat change. And that's where, if we look all the way at the bottom, that was the equation we talked about before when we rearranged, where we have the specific heat, we have the mass, we have delta T, and then we could solve for the energy change. Specific heat for water is 4.184 joules per grams Kelvin. And for these dilute solutions, that's typically the value you use as that CS value there in the formula. So this is what I was saying before. A lot of these heat capacity numbers are known. They've been experimentally determined, and you can look those up and plug that in. So this is a way where you would then be able to determine if you had exothermic or endothermic. So if the reaction gives off heat, is that exothermic or endothermic? Does anyone remember?
Exo, no endo.
Which you're going with? Gives off heat, exo or endo?
Endo.
Endo. Any other thoughts on that? Okay. What do you?
Exo.
Exo. Yeah, it's exo. So I always think giving off, I think exhale, something like that. Endo, in, going in. So if you're putting energy in or putting heat in, it's endothermic. If it's giving it off, it's exothermic. We had the one example of I think it was potassium, metal, and water kind of exploding as an exothermic. Okay, bomb calorimetry is another type of calorimetry. So we showed you the picture of the kind of simple with the styrofoam cups and that, and that's good for Gen Chem labs, and maybe even in high school, you may have done that experiment. And it's a good way to kind of illustrate some of this stuff. But when you really are doing it a little more seriously, I would say, and want a little better quality data, you'd use something like a bomb calorimeter. And so it's not as scary as it sounds. It's just it's usually, these things are really heavy metal, really well insulated. And you can kind of see there where there's ignition wires and it's down in a beaker. Sometimes you have water surrounding the beaker, sometimes you don't. It depends on what kind of experiment you're doing. But you have oxygen in there in that reaction chamber. And what you do is you basically blow the stuff up, okay, on a real small controlled scale. And you get a temperature change there. And there's different variations of these bomb calorimeters, but in essence, that's what happens. And so you measure either the heat that's given off in that reaction or the heat that goes into it in the reaction. And once again, that would tell you if it's endo or exothermic. The one thing about this is if you look at the formula at the bottom, it's a little bit different because you have this minus C with a CAL subscript. For these types of experiments, you have a constant that pertains to the system, to the calorimeter. So that's the calorimeter constant. And that's something that you determine experimentally by running something that you know the answer to and basically seeing how far off you are. And then that gives you a feel for what the impact of the calorimeter is. So, like I said, this is the type of equipment that people would use to generate those numbers that we would find in the tables and stuff like that. This is also one of the ways that they do, like if you ever see there's so many calories in food or whatever, this is a way you can determine that by doing bomb calorimetry. One note on this is that because the volume in the calorimeter bomb calorimeter is constant, technically what you're measuring is internal energy, the change in internal energy, delta E, not delta H, but in reality, they're pretty much the same thing. So. Let's move on to something called Hess's law. And because delta H is known for a lot of reactions, and it would be a lot of work and a kind of a pain in the neck to analyze, to experimentally determine delta H every time you had a new reaction, is that there's tables of these delta H values for reactions. And what you can do is you can calculate delta H for new reactions using the information in these tables. And that's what we're going to talk about here a bit. So if a reaction, what Hess's law tells us is that a reaction is carried out in multiple steps. So a lot of times reactions are you mix A and B and you get C, but other times you mix A and B and you get C, and then C reacts with some, you get D, and on down the line. So there's different steps before you get to the final product. Hess's law tells us that delta H for the overall reaction is the sum of all the enthalpy changes that occur along the way. So whether it's a one-step reaction or a four-step reaction or whatever, it's a state function. So all that matters is the beginning and the end. It doesn't matter how we got there. Remember, we talked about that a little bit on Monday. The process of getting there isn't as important as the end result. And so through Hess's law, we know that whether it's a simple one-step reaction or multi-step reaction, if we add up the H's in those, we should get to the same point. So that delta H from start to finish will be the same, whether it's one step or multi-steps. Because of that, we can use these reactions that have been determined already to kind of add things up and get to what it is for the final reaction product. Okay, there's a bunch of homework associated with this. There's a few here that I want to go through with you so you can get a feel for how these problems are done. And so that's what we're going to do now. You know it's a special day because I even brought my book. It's the first time I've lugged this thing in. So okay. So that's not too bad. Okay, so the first one, 5.43 that we're going to go through. So in this, we have the reaction up top. That's the magnesium plus oxygen gives magnesium oxide. And it tells us what the delta H is. So it's minus 1204 kilojoules. So if delta H is negative, is that exothermic or endothermic? Exothermic, yeah. Remember, negative is exo, endo is positive. So we know that right off the bat, that this is an exothermic reaction. And so then they want us to calculate the amount of heat transferred when 3.55 grams of magnesium reacts at constant pressure. So we know we want to get to heat, right? Which is going to be joules or kilojoules or something like that. We're starting with a mass, and we know something about the reaction stoichiometry, right? The stoichiometry, remember, is the coefficients in front of each of those molecules. And the first thing, when we talk about grams and we want to get into some other unit, the first thing we should be thinking about is I may have to be getting something changed to moles here. So that's where I would need to know molecular weights, atomic weights, things like that. So if we look at this, if we start with 3.55 grams of magnesium, if we look up the atomic weight of magnesium is 24.3. And so now we've converted it into moles. Because we're into moles now, we can use that to get a feel for the energy that's involved. And we were told that for this reaction, delta H is minus 1204 kilojoules. But if we look at the reaction stoichiometry, we see that 2 moles of magnesium is what's involved in this reaction. So that's why when I go have my moles of magnesium, then the next one, the denominator has 2 moles of magnesium. It's because of that coefficient on front of the magnesium in my equation. So that tells me that 2 moles to get to this minus 1204 kilojoule delta H value, it had to have 2 moles of magnesium reacting from the reaction. So then I ratio that, the minus 1204 kilojoules divided by 2 moles. And then now my units all cancel. My final units are kilojoules. And it comes out to minus 87.9. Any questions on what we did there? Yeah.
Was the 3.55 grams of magnesium from the question?
Yes, it was. Yeah. They told us that. The question was, let me read it again for you. Let's see. Where'd that go? Yeah, it said calculate the amount of heat transferred when 3.55 grams of magnesium reacts at constant pressure. So once we saw that we're starting with grams and we want to get to that energy number, then we knew we're probably going to have to go to moles to take advantage of some of this stuff. Okay. All right, let's see. What are they asking us to do in C? How many grams of magnesium oxide, that's the MgO, are produced during an enthalpy change of minus 234 kilojoules? Okay, so if we're at minus 234 kilojoules, and now we're interested in magnesium oxide, so we're thinking we want to get from, in this case, energy, kilojoules, we want to get to grams. So once again, we know moles are going to be involved, and we know the stoichiometry is going to be involved as well. Kind of similar to what we talked about in B. So on C, that's that minus 234 kilojoules that they gave us in the problem. We start with that. We know our delta H is minus 1204 kilojoules for this reaction. Since we're with magnesium oxide, we're looking and we're saying, okay, our stoichiometry, there's a 2 in front of the MgO. So similar to on the previous problem, we have to have 2 moles of that are involved in this reaction, this minus 1204 kilojoule reaction. So now we're in units of moles of magnesium oxide. The 40.3 is the molecular weight of magnesium oxide. So if we looked up the atomic weight of magnesium and added it to the atomic weight of oxygen, that's 40.3. So I've taken that amount of energy they talked about and converted it to moles of magnesium oxide, because that's what we're dealing with. Then converted the moles into grams, and I get that final answer of 15.7. So you see some common themes here. You see themes of changing things into moles. So you need to be able to calculate out the molecular weight of the compounds. We see that the balanced chemical reaction, those coefficients on the front are real important, because that tells us how many moles of the different reagents are involved. And then we use that information, kind of piece it together. This is where the dimensional analysis comes into play, is if you line things up correctly and your units are out canceling, you're probably going to be in pretty good shape. Then it's a matter of being careful with your calculation, using your calculator and getting that right. Okay, let's look at D then. How many kilojoules of heat are absorbed when 40.3 grams of magnesium oxide is decomposed into magnesium and oxygen at constant pressure? So 40.3 grams magnesium oxide. What's the first thing you notice that's different about that statement versus the other ones? Is that now we've been looking at this reaction as a formation reaction of magnesium and oxygen forming magnesium oxide, right? Now we're talking about the reaction going the other way. If you recall, one of the things we talked about is if the reaction going this way is minus 1204 kilojoules, the reaction going the other way is the same magnitude, but it's the opposite side. So this is exothermic going from magnesium plus oxygen. If we're decomposing magnesium oxide, then we're going to have to put energy into that. And so that won't be exothermic, that'll be endothermic, so the sign will change. So that's why when we go to the bottom here, first thing, we change those grams of magnesium oxide to moles using the molecular weight. Then we use the stoichiometry of the equation to see how many moles of it go with this delta H value, and the answer is 2. But you notice the sign on that isn't negative 1204, it's positive 1204. And that's because the reaction now we're talking about is that decomposition reaction. And we said before that delta H, whatever sign it is going one way, if you go back the other way, the magnitude stays the same. So in other words, the number stays the same, but the sign changes. So that's why on that one, the sign is positive in that. And you see our answer is actually plus, what is that, 602 kilojoules. Any questions on any of these? Yes.
So 2 moles comes from the fact that it's the 2 in front of the Mg.
Yes.
So rather than like a 3 or a 4, it would be 4 moles or 3 moles.
Yeah, the 2 on this last one comes because the MgO over on the right-hand side has a 2 in front of it. And so that tells me that in this reaction, 2 moles of it are involved. So whenever the delta H was determined, 2 moles of that material was part of it. So I have to keep that in these calculations. But you're right, if that was a 3 or a 4, then it would be 3 or 4 in the problem. Any other questions? Okay. Let's do some more problems. This is a specific heat problem. This is number 551. And so, just to remember, when we talk about specific heat, it's the quantity of heat transferred divided by the grams of substance divided by temperature change. And so that's where we get our CS is Q over M delta T. T is usually Kelvin, Q is almost always joules, M is usually grams. The temperature can be T or can be Kelvin or C. The value for water is 4.18. That's something you would just look up in a table. But the other questions that they had for us were, what is the heat capacity of 185 grams of water? Okay, so in this case, we want to convert it to grams per mole. And so we do that by using the molecular weight of water. So the molecular weight of water is 18. And so by having 18 in the numerator, 18 grams per mole, we see our grams cancel. And now we're at 75.4 joules per mole degree Kelvin. So once again, that's simply a dimensional analysis problem. Then in C, oh wait, that was the molar heat capacity. C is, what is the heat capacity? 185 grams. And so 185 simply just multiplied by that. So your grams cancel. And then D is, how many kilojoules of heat are needed to raise the temperature of 10 kilograms of water, 24.6 to 46.2? So on this one, it's the same formula, but there's a couple of things we have to do. One is, if you look at the bottom, I have, for mass, I have 10 times 10 to the third grams. Why do I have that? It told me there were 10 kilograms. Why do I have 10 times 10 to the third? Yeah.
Because 10 to the third is like on the table you had last time. 10 to the third was for kilograms.
Yes.
6,000.
I had to convert that kilograms to grams. And so if I'm going from kilograms to grams, that's 10 to the positive third to do that conversion. Because 1 kilogram equals 1,000 grams. So this is a case of where I need to look at my units on my energy units, joules, grams, Kelvin, and have to be able to cancel those out. The temperature change, I have 46.2 minus 24.6. What's going on there? Didn't I say it has to be Kelvin? Why am I using centigrade? The reason why you can get by with that is because it's a difference calculation. And the scales, if you add 273 to each of those numbers, okay, which is what you would do to convert it to Kelvin, and did the subtraction, you would get the same number as just subtracting the centigrade. Because centigrade and Kelvin scales are the same number of digits in between the freezing and boiling points. So the scales are the same. It's just 273 added to it. So if you want to be 100% safe, you could add 273 to each of those and do the subtraction, but you're going to get the same number in this case. So you would then rearrange this to solve for Q, and you would get 903 kilojoules. So if it's kilojoule, but my 4.18 is in joule, what did I leave out here? It doesn't make sense to me. I had joules, but now I'm saying it's in kilojoules. I didn't write it all out, but what did I do here? If you want to go, what's the difference between joules and kilojoules?
There's 1,000 joules in a kilojoule.
Right, 1,000 joules in a kilojoule. So really, this would be 903 times 10 to the third joules, if you wanted to look at it that way. Okay, any questions on this one? Yes.
B, where did the 18 come from?
The 4.18,
No, where'd that 18 on the side of it come from? And B.
oh, on B,
Mhm.
that's the molecular weight of water.
Ah.
So oxygen is 16 and hydrogen is 2. So that's where the 18 comes from. On that one, we were trying to express it on a molar basis. So we needed to change the grams to moles. Okay, any other questions on this one? And remember, these homework problems are all posted. So if you want to go back and take a look at them later, this is out there. Okay, let's look at 553. So in 553, they're telling us that the specific heat of octane is 2.22 joules grams Kelvin. The first question is, how many joules of heat are needed to raise the temperature of 80 grams from 10 to 25 C? So we think back to that formula that we used, where we have in this case, the 2.22, which is what we were given, that specific heat value is what we were given, equals Q over the mass times delta T. So the mass we were told was 80 grams. Delta T will be that 25 minus 10. And then if we rearrange this, we can solve for Q. And in this case, you can see I said it's either 2.66 times 10 to the third joules or 2.66 kilojoules. And we made that conversion, I actually wrote it down this time instead of just doing it. So once again, we're setting stuff up so that we're making sure everything's in the right units, and that heat capacity number that they gave us, that gives us a feel for, are they talking about it on a gram basis or a molar basis or what basis? So that's why we knew here we didn't need to change anything to moles or anything like that. Let's look at B now. So in B, it asks us which will require more heat, increasing the temperature of 1 mole of the octane by a certain amount, or increasing the temperature of 1 mole of water by the same amount. Okay, so if we have 1 mole in the first part of B, if we have 1 mole of the octane, we want to convert that into grams because of our constant. See, our constant has a grams unit. And so the 114.2 is the molecular weight of octane. So if we did 8 times 12 plus 18 times 1, that should be 114. So now we've converted moles of octane into grams of octane. Then we use the constant that we were given, the 2.22 joules grams Kelvin. We do that math and our gram units cancel, and now we have joules per Kelvin, and we get 254. We do a similar exercise with the water, where we would take 1 mole of water, 18 is its molecular weight, and then we know from before what that constant is for water, 4.18, and we'd use that and we'd get 75.4. So if the octane is 254 and the water is 75.4, that's a bigger number, so we know it's going to require more heat, more energy for the octane. Okay. Any questions on this one before I go to the next one? Yeah.
On A, on the bottom, or on the denominator, 25 minus 10, is that the temperature change?
Those are the two temperatures that we were given, yeah. So that's the initial and then final temperature.
Okay.
So that's our delta T there. Yep. And like I said, I know I harp all the time if you got to have right units. This is like one of the few calculations, because it's a delta T calculation, that whether it's C or K, it doesn't matter. It's just that difference that since you're not depending on the absolute temperature, you know, that number, it's just that difference number. You can get by doing that. So that's probably not setting a good example for you guys, but it doesn't matter in these calculations. Okay, let's look at 5.57. Okay, so this is a bomb calorimeter one. So you have 2.2 grams of quinone, and it's burned in the bomb, and the bomb has a heat capacity of 7.854 kilojoules per C. The temperature change in the calorimeter is 23.44 to 30.57. And it wants to know what's the heat of combustion per gram of quinone and per mole of quinone. So the formula we're going to use, we're going to get this heat of reaction from above there, where we were told that the constant for the calorimeter we're using is 7.854, and we know what our temperature difference is. It's that 30.57 minus 23.44. So we take the calorimeter constant that we were given, change the sign, because that's part of the formula to change the sign, and then have our temperature difference. And we get a value of 560 kilojoules. If we then want to calculate out what that is per gram, then we simply take that number, and we were told that we had 2.2 grams of quinone in our reaction, and we divide it by that. So that gives us minus 25.5 kilojoules per gram. If we want to express it on a mole basis, we simply would take the 2.20 grams, we'd calculate out what the molecular weight of quinone is, and that's 108.1, and then convert that to moles. So then we'd have moles, kilojoules per mole, rather than kilojoules per gram. So this is a negative number. Is this reaction exothermic or endothermic? Exo, right, because it's negative. Any questions on this one? Okay. Okay, so let's look at 5.65. This is an example of the type of calculations you would use Hess's law for. Remember, we said Hess's law, if we know individual steps along the way, we can use those delta H's to get what it is for the whole reaction. So in this case, we have our reaction written on top, C2H4 plus 6F2, 2CF4, 4HF. What we can do is we can look up the reaction, some of the reaction steps that occur along the way. And that's what we have on these next ones. And so these reaction steps were given in the problem along with the delta H values for them. And so those numbers on the right-hand side, the minus 537, minus 680, plus 523, that kind of information would be given to you. So that's the delta H for each of those reactions written that way. What we would need to do is we would need to rearrange these reactions. And by rearrange, I mean either flip it so it goes the other way, or change the coefficients in front so that we wind up with that top reaction. So if we just kind of start left to right on that, we see the first one, C2H4 on the left. So I've written that first reaction, the C2H4, I've flipped it around so that the C2H4 is on the reactant side. Okay? Because I did that, I needed to change the sign on the delta H. If you look over on the right there, it was plus 52.3. And now, and that was when it was 2C plus 2H2 going to C2H4. Since I flipped it around to match that top reaction, I had to change the sign from plus 52.3 to minus 52.3. Once again, this is what we talked about, is that delta H, the number doesn't change, the sign changes if you flip the reactions back and forth. Then the next thing I know is I need F2 on the left. So I take that H2, F2 reaction, have that on the left. Same with the CH2 one, I have the F2 on the left. So those two are okay on the left. And now I go and I look and start seeing the numbers. I know I have to get to a total of 6 for the F2 molecules. I have to get 2 for the CF4, 4 for the HF. So that's where I go in. And so like in the second one I have written there, everything's multiplied by 2. And this is so that I can get to the numbers that I need to have the right total. Okay? Then what I do is I go and I cross out the things that are the same on each side, kind of similar to the spectator ions we talked about on some other things. And if you then add things up, you see C2H4 plus 6F2 going to 2CF4 plus 4HF. That is the same reaction as the one at top that we said we're doing. So the other thing you'll notice is, because on these second and third reactions, I had to multiply them by 2 to make the coefficients fit. I had to multiply the delta H value for each of those by 2. So there's a lot going on here. The key thing is, before you worry about the numbers, you have to get these intermediate reactions set up, first of all, if they're going the correct way. So the third one, the 2C plus 2H2 going to C2H4, that reaction's going the other way, the wrong way. So I had to flip that around. That was the first thing. Then it goes back to kind of managing the coefficients so that everything's going to cancel out and come to that final reaction. To do that, I had to multiply the other 2 reactions by 2 to get everything to cancel out correctly. Because I did that, it tells me that I have to multiply by 2 the delta H values for those. So if I got all that right, then it's a matter of adding minus 52.3 plus 2 times minus 537 plus 2 times minus 680. And then I should get that kilojoule value that's there. This one can be a little confusing, so definitely practice some of these, okay? Because like I said, you've got a couple things that you're doing here. One is you're trying to first decide which way the these intermediate reactions are going. Are they going the way they're written, or do you need to flip them around? If you flip them around, then you got to change the sign on that delta H. Then the next thing you got to do is you got to get it all balanced. So kind of similar when we balanced equations before, we got to get it all balanced, and at the end, cross out the things that are the same on each side, and we should wind up with that same net reaction as we had, as what we said was the reaction overall going on. So the other thing is on that reaction on the bottom, it should balance, and it does. So that's something with the balancing of the reaction that's pretty easy to check when you're finished, just by going back and checking the coefficients and things like that. So this is a Hess's law type problem. You're going to see this again, either on a quiz or test, okay? Any questions about this one? Yeah.
So when you flipped C2H4 and 2C and 2H2, is that because on the left side of the original equation, C2 and H4 were on the left side?
Yes.
Okay.
Yeah, because if I left it like that, if we just added all those together, I don't have any C2H4 on the reactant side of my equation up top. And so the only place where C2H4 shows up is in that third half reaction, the third one. And so if I flip that over, then now I've got the C2H4. I've got F2s on the left-hand side from those two reactions, the first and second half reactions. So I'm good there. So that tells me I've got C2H4 on that side, I've got F2 on that side. And so the other thing you may notice about that is, and this is where the canceling out comes in, I still have H2 and I have C on the left side, just by doing that one flip of the third one, right? And I don't want those up top, but they're not on the right-hand side either. So as long as I have them on both sides, it tells me that if I get it balanced correctly, they're going to cancel out and I'll be okay. It's kind of like doing a puzzle, to be honest with you, kind of flipping it around and piecing it together. So I know you're all smiling at that comment, but I just can't see it because of the mask. So, okay, any other questions about this one? Okay, so we're going to stop on the homework for a second and talk about some other things. Okay. So the funny thing about delta H, about enthalpy, is everything's got its own enthalpy, right? So you'll get sick of seeing delta H with another subscript. And here's another one for you. There's more to come. So delta H with a small f subscript is the enthalpy of formation. And that's defined as the enthalpy change for a reaction in which a compound is made from its constituent elements in their elemental formulas. To be honest, most people call it heat of formation. So this is telling us to form a particular compound from its most base way. What's the delta H on that? So the heat of formation is the one that typically people say. Okay. These standard heat of formations, enthalpies of formation, are measured under constant conditions, 25 C in 1 atmosphere. That's another thing you see all the time. There's always, when they do these experiments, it's really restricted in terms of what the conditions are, because these things aren't easy to do. So they lock certain parameters down. In this case, 25 C, 1 atmosphere is what's usually used. And these are just some values here. You don't need to learn these. You don't need to memorize these. This is just here to show you for various compounds, kind of the range of things. So it just shows you that it's a wide range. Some are exothermic, some are endothermic, a wide range of values. Okay, But what is important, again, like we talked about, and this is kind of a continuation of that Hess's law thing, is that when you have reactions going on and you're calculating delta H, it's a lot of times there's stepwise fashion to it. And the nice thing about it is, by knowing values for those individual steps, you can piece it together to get it for the whole reaction. That's the main takeaway here. So for this reaction up top, let me just go back a second. So this C3H8 plus 5O2 going to 3CO2 plus water. What kind of reaction is that? Does anyone know what kind of reaction that is?
Question.
Combustion, right. And you knew that because you saw the O2, right? So in this case, this is propane. This is your Bunsen burner reaction. So you can break it down into steps where you have the propane gas going to carbon and hydrogen, form CO2, and there's that. Then you form water. And so you have all these steps in there that you have. And so you can have delta H values for all these. And you can use that information. And so here, once again, if we sum up these equations and cancel out the stuff on each side that cancels and that, for instance, like the 4 H2s on each side cancel out. Lo and behold, our sum reaction is the same as what we said our overall reaction was. So that's a good thing. And so then we can use Hess's law to say that the sum of the products minus the sum of the reactants, so the delta H values for the products minus the delta H values for the reactants, that's delta H for the overall reaction. So we use that information from those side reactions, those intermediate reactions rather, to add up and use this formula to get this. The N and M, that's the stoichiometric coefficient. So once again, going back here, like that's like the 5, the 3, the 4 on these. We would use those. We would use the stoichiometric stuff to get a feel for what the delta H is. So, okay, here's an example. So we said it's, just to remind you, we said it's products, the sum of the products minus the sum of the reactants. So we would look these values up in a table, in an enthalpy table. And so if we have, let's sum up the products first. So the products were 3 CO2 plus 4 H2O. So on the first bracket of things that we're adding together, it's 3, because 3 moles of CO2 times minus 393.5 kilojoules. That's that delta H value we would have got out of the table, plus 4 in front of the water, times minus 285.8. Once again, that's the number we would have gotten out of the table. So we sum those up. That's what those brackets mean. Then minus, we're going to do the reactants now. 1, because 1 mole of propane times minus 103.85 plus 5 times the O2 one. The O2 one, those diatomic things are always 0, but we get that out of the table. So 5 times 0. So we go ahead and do the math, and that's what these next 2 steps are. And we would get to minus 2219.9 kilojoules. So just to remind you of what we did, we summed up the products, the delta H values from the products, and then subtracted the delta H values from the reactants. And we used those coefficients in our formula to know if we needed to multiply each of those delta H values by anything. So in this case, 3 in front of the CO2, 4 in front of the water. That's where the 3 and 4 come from on the product side. And then on the right-hand side, the reactant side, We have 1 propane, 5 oxygen, and so 1 and 5 are the coefficients there. Any questions about those? Okay. So now we're going to talk about something called bond enthalpy. Like I said, you're going to get sick of all these different enthalpies. And bond enthalpy is usually associated with breaking 1 mole of a particular bond in a gaseous substance. Bond enthalpy is always positive because to break a chemical bond, you have to put energy into it. Okay, so that's always an endothermic process where you got to put energy into it. Now, energy is always released when a bond forms between gaseous fragments. The greater the bond enthalpy, the stronger the bond. So key takeaways here, they're always positive, and these are some bond enthalpies. They're always positive, and bigger they are, the stronger the bond. So if you're not familiar with which things are bonds, this is a good table to look at, because you'll see in a little bit when we do one of the homework problems, you got to be able to identify the different bonds. So like a CH bond, a CC bond, a C double bond C, things like that. Okay, so to calculate, we can estimate a delta H of reaction by looking at these bond energies. And so the formula is we have bonds broken minus bonds formed. So which ones are the bonds broken? Those will be the bonds that are on the reaction side, right? On the reactant side. So the reactant side, we look at all those bonds and we'll look up their bond enthalpies and we'll sum that up. Then on the bonds formed, the product side, we'll look up all those bonds and their associated bond enthalpies and add them up. And so we'll have the ones formed, we have the ones broken minus the ones formed. So we could use this information to predict what's going to happen. I think it works sort of, but a couple of things I just want to talk about is in food, you hear about energy and food and all that. So here's a table that just shows what's the composition of the food. And then in terms of the fuel value, and that's really that like kilojoules per gram value. Or if you want to have calories, kilocalorie per gram. It just gives you a feel for some of the relative things on that. So what the takeaway I always get from this one is fat's a really good source of fuel. So fat in your body, that's why it's important. It's really a good fuel source for you. This is fuel values here for energy type stuff. And it gives you a feel for how good a fuel different things are. And what you see is hydrogen's a really good fuel. That's why you'll see some of these hydrogen vehicles around, because it's a really good fuel source. But the natural gas, gasoline, things like that. Coal, which there's always a lot of controversy about, really isn't as good a fuel source as some of these petrochemical things. And wood is even further down the line in terms of fuel source. Okay, let's go over a couple homework problems here. So first one is 573, number part D. So in this, you're being asked to calculate the standard enthalpy change for the reaction. And so these enthalpy values that you're using, you would look up in the table. So I've written out the reaction, and underneath it, in parentheses, the bigger number is the enthalpy value for that compound. Okay, so that came out of a table. I have a 2 in front of the water one and a 4 in front of the HCl one. Why did I do that? I did that because of the coefficients in my reaction. Okay, it's saying in this reaction, it's 2 moles of water, 4 moles of HCl. So I need to reflect that in my formula when I do the math. Remember in the formula, it said there was N and M, and that's the coefficients for the compounds. So then for delta H reaction, it's products minus reactants. So I take the not minus 910 plus 4 times minus 92.3, and then subtract from that the reactants, which is minus 640.1 and 2 times minus 285.83. Yes.
You said those numbers are from the tables?
Yeah, so like the 910.9, 92.3, those would be in a table.
So the 640, is that the molecular weight?
No, 640 is the same. All those numbers, all the big numbers of those 4 numbers, those are all the delta H numbers for those compounds.
So they're usually given to us?
Yep. Yep. So you would not be expected to know those numbers. If you do, then you probably have a photographic memory. So, any other questions on this?
Which table did you get this from?
I forget, it's in the back of the book, I think. I think it's like Appendix C or something like that in the back of the book. It tells you in the problem. In the problems, it either says, here's the numbers, or it says you need to go look it up in the back of the book. Okay. Okay. This problem, this 583, is one where we're using bond energies to get an estimation for the delta H for the reaction. And so, let me just make sure I'm not missing something when I go through this, but. Yeah, no, so in this case, it tells you table 5.4 has the bond energy. So what we want to do is we want to first segregate things into bond breaking and bond forming. Bond breaking is the reactants. That's everything on the left. And so let's look at the first compound. First thing you should notice is there is a coefficient of 2 in the front of it. So drop back down there, and there's a 2 there. Then I have that the bond I'm looking at is the CH bond. And the way it's drawn in that first molecule, you can see 3 CH bonds in that. Does everyone see that? So then that's why there's 3 of those. So there's 2 moles of the compound. There's 3 CH bonds in that compound. And then 413 is the bond energy for CH. So that's that first term. I'm still on that first compound because I've got other bonds. The next one I'm looking at is a CO bond. See the C attached to the O. Once again, I have a 2 in front because there's 2 of these molecules, 2 moles. That 358 number is the number I would have gotten out of the table for the CO bond. And then the third bond, type of bond that's in this molecule is an OH bond. So once again, 2 because there's 2 moles, and then the OH bond energy is 463. So that takes care of that first molecule. All 3 of those things go into the bond energy calculation for that first molecule. Then the next is O double bond O. So there's a 3 coefficient in front of that. So I have 3 times that bond energy, which is 495. All of those are the bonds in the reactants. So I have to calculate all those up and sum that up to have my bond breaking part. Remember we said in this, using this formula, bond breaking minus bond forming. So now I'm going to do the bond forming part. The first molecule on the right-hand side is C double bonded to an O. I have 2 moles of those. So there's a 2 out in front, and then there's 2 of those types of bonds. So that's where I get 2 times 2. Then 799 is the bond energy for that particular bond. And we'd have got that value out of the table. So I've got that molecule done. Now the last one is water. And in water, we see we have 4 moles of that. So I have 4 coefficient out in front. And then I have 2 OH bonds in there. So then it's 4 times 2, and then 463 is the bond energy for OH. So I would do the math on the bond breaking, add that up, and then subtract the math from the bond forming. And if I do that correctly, I get minus 1295 kilojoules. So this is the basic approach that you do for these kind of bond energy calculations to see if the reaction, what the reaction is doing, to estimate the delta H for the reaction. You need to have the molecule drawn out in this kind of stick-like structure so you can see where the bonds are. And then count the bonds, see how many moles of that molecule are involved in the reaction and factor those in, and then you look up the bond energy. Any questions on this? Once again, I would suggest that you look at some of the other problems that are similar to this and practice a few times so you're comfortable kind of going through this. Yeah.
On the farthest for
Yeah.
OH,
Uh-huh.
how come there isn't a 2 there? Because isn't that O going to, there's 2 OHs?
There is. So if you look down there, it's 4 times 2 times 463.
I was looking at the top thing.
Yeah, the top one is the bond breaking. So that's everything that's a reactant. So that's the left-hand side.
Okay.
And then the right-hand side is the bond forming. That's the products. So but you're exactly right. There needs to be 2 because there's 2 OH bonds in that molecule. Okay. Any other questions? Okay, I think that's it for today then. Monday, we'll do a review of chapters 3 and 4. I did go ahead and I posted the homework answers to chapters 3 and 4. So if you want to look at any of that when you're studying. And then next Wednesday, we will have an exam.